So the working principle for a DC generator is not that difficult. It's Faraday's law, essentially. You take let's say, a rectangular loop of conducting wire, rotate it in a magnetic field, you get EMF across the two ends of it. That's it. It is the implementation where a lot of challenges exist and a lot of them have been solved successfully. The three things that you need to make a DC generator are conductor or conductors, because in general one conductor will not give you enough EMF, so you have several of them in parallel and in series to get the required voltage and current. You need a magnetic field in which to rotate the conductor, and you need the rotary mechanical input which is going to rotate the conductors, which typically comes from a turbine, especially in big systems, or it can come from a diesel generator, or it can come from several other possible sources, wind turbines, etc., etc. The source of mechanical power is also given a name called prime mover, PRIMEMOVER. We'll come to all that in detail later. Today I'm giving you an overview first. So the working principle is Faraday's law, as I said. When you move a conductor in a magnetic field, you get an EMF across the two ends of the loop that you have made out of the conductor. Okay. If you connect something across those two ends, you will get current flowing in that circuit. Now, in practice, more than one loops are always used. What we do is, this is a 3D pictorial diagram, and we have opened part of the construction to show you some details. The magnetic field is created by north and south poles, which are essentially created by using magnets on the inside of a circular frame called stator. Normally, we use more than two poles. The number of poles has to be even, because for every north pole, you need a south pole also. So you have to use minimum two poles. It can be 4, it can be 6, it can be 8, and so on. Okay. So those guys will produce the required magnetic field. That is known as stator. It doesn't move. Then in the inside, you have something called a rotor, which is being driven by mechanical energy input. There's a large amount of conducting loops on it, which generate the required electrical power. The electrical signal that comes out is actually AC. And we convert that into DC using a mechanical rectifier called commutator. I'll be going into details of all this later. And the entire construction is housed in a body called yoke, Y-O-K-E, which is generally bolted on the floor of the factory or floor of wherever you want to use it. So that's roughly the construction side of it. Now the magnets that you are using on the inside of the outer part of the body, which is stator, those magnets can be made out of naturally available magnetic materials. That's one method. Or they can be electromagnets. For small power requirements, natural magnets are okay. For example, children's toys, they use DC motors and they use natural magnets. But for large power generation or even for large DC motors, natural magnets are not strong enough. They don't produce enough magnetic field. So what we do is we take those natural materials and put wires on top of it, current carrying wires. to produce much stronger magnetic flux. And those things are called as electromagnets. The wires on the magnets are known as field windings. The wires on the rotor, which are the conducting loops, which are rotating, they are known as armature windings. The rotor essentially has mechanical and electrical part. It is made of magnetic material again, as in transformers. And the core of the rotor is laminated, as we saw in case of transformers, that reduces the eddy current loss. On the outer part of the rotor, we house all the rotating conductors in slots. That outer part is known as armature. Essentially speaking, the electrical part of the rotor is known as armature. So windings or loops on the rotor are known as armature windings. Shaft is shaft, it's a cylindrical thing that comes in carrying the mechanical power in, rotating mechanical energy input, and that helps in rotating the rotor. Okay. This is the cross section of the same thing. Field windings, you see a lot of poles, a lot of magnetic poles are there on the outer periphery, inside of the outer periphery. The outermost part is known as yoke. Then we have stator, which is housing all the magnetic poles. And magnetic poles are carrying windings on them, which are known as field windings. Then in the insides, you see a circular cross section, which shows you the rotor. On the outermost periphery of the rotor, you see a lot of slots housing the various loops or conductors. And on the inside, you see also something called commutator, which helps in converting the generated signal into DC, as well as magnetic material is there to get better efficiency out of the system. Of course, the core has to be laminated to reduce the eddy current loss. We'll come to all that in detail. Right now, just appreciate the bigger picture that essentially you have got magnetic poles energized by field windings. You have current, you have loops of conducting wire known as armature winding, and they are rotating. They are cutting the magnetic field produced by the poles and generating the required EMF. The connection to pick up the voltage being generated is done through what we call brushes. They touch the rotating part and pick up the required voltage. The speeds involved are generally quite high. So brushes have to be very carefully designed. Wear and tear happens all the time in brushes. I'll come to that in the next slide. But first, yeah, here, the word brushes is mentioned here. These 5 are the core requirements in the construction of a DC generator. Field system produces the required magnetic field. Armature core is necessary for housing the windings on the armature. Commutator converts the AC signal into DC signal, and brushes pick up the voltage from the system. As I said, number of poles has to be even, 2, 4, 6, etc., etc. Okay. This is actual construction. We are not showing the rotor here, only the stator is being shown. Probably you don't see everything in detail, but you can see that electrical wires are being wound on magnetic materials to produce the required magnetic flux inside the construction. The rotor will be brought in after this. Another view This is the rotor side. The rotor has a lot of conductors on it. They all come out from the slots, and there is a assembly called commutator, which helps in converting the AC voltage into DC voltage. Lot of segments are there. One pair of segments essentially handles one loop of wire. There's a lot of detail in terms of rotor construction, there's too much detail. It's impossible to go through each and everything in a PPT like this. But I appreciate the fact that implementation of Faraday's law takes a lot of effort. That is the essential message I'm trying to give you. Smaller generators are usually easier to build. Bigger ones require a lot more effort, obviously. Commutator also rotates continuously, and to it brushes connect and pick up the voltage. Brushes are not rotating. Motor is the opposite of the generator. Here, what you do is, instead of rotating the rotor, you actually supply DC input to the rotor. And the functionality is reversed. The rotor starts rotating because of the interaction between the field generated in the conductors of the rotor and the field produced by the stator. So motor is the opposite. We'll come to motor in detail later. Now, working principle, whether it's motor or generator, the working principle is hardly any different. Let's stick to generator for now, and let's see the theory in detail once. Suppose I have got only two poles, one north pole and one south pole, producing a magnetic flux between them. And I have only one conductor, rectangular loop has been made out of it. The two ends of the loop, let's say, are connected through some suitable mechanism to a resistance. Now, if the position of this loop is that shown in figure A, that means the loop is vertical. That means it is at 90 degree to the direction of the flux. You will get, if you don't put commutator in the system, then you will get AC voltage out of this. And that is what we are showing in the diagram below. A is going to give you 0 EMF. Position A will give you 0 EMF. Essentially, the conductor or the loop has to be rotated at a constant rotational speed. We measure it by using revolutions per minute, RPM. I think you know that. A constant RPM will give you a constant frequency of the AC signal being generated. When we convert it into DC, that's another story. But theory says that the frequency of the AC signal generated will depend on the RPM at which the loop is being rotated. That's common sense. Suppose the loop starts from position A, you'll get 0 EMF. Then in position B, it has now become parallel to the flux. You will get maximum EMF. That is position B. We call that 90 degree angle. Then the loop goes to 180 degree angle. That means position C. You will again get 0 EMF. And then the second half, which is the negative half of the cycle, is obtained for the rest of the rotation. I'm talking about one full rotation of the loop. There's a lot of electromagnetic laws that will prove this, but you don't have to worry about them in this course. Important thing is that one full rotation of the loop will generate one full AC cycle. Okay. So if the rotation is happening at 1 revolutions per second, the AC signal will have a frequency of 1 cycle per second. Okay. If you are rotating at 1 RPM, okay, then you have to calculate what frequency will be generated. Anyway, right now we are going to anyway convert the signal into DC, so we don't have to worry too much about frequency, etc. But when we go to AC machines, we'll see that frequency of the signal generated will also be a concern. Right now, don't worry too much about calculating the frequency. Right? But important thing is that one loop alone will give you one cycle in one when it rotates once. Okay. Now the EMF generated will not be very large. It will be very small value. So we put thousands of loops in parallel to improve the value of EMF. In fact, to improve the current carrying capacity or current generated out of the system, we also put a lot of loops in series. We'll come to that later. But the basic theory is what I'm trying to show you here. It's Faraday's law that you are seeing. Now forget about nature of windings. I'll come to that later. Field system, that means how to generate the magnetic flux. As I told you, electromagnets are preferred compared to naturally available magnets, because naturally available magnets, they don't produce sufficiently large magnetic flux. They also age very fast. Within a year or so, you'll see that their magnetic flux has decayed severely. So for most practical DC generators, we have to artificially stimulate the magnetic material by putting windings on it. And those windings, as I said, are known as field windings. Okay. Field strength can be varied. If you are putting windings on the magnets, then you can change the current going in those windings. That way the flux generated can be changed also, if necessary. That will not be possible if you are using permanent magnets. That means naturally available magnets. They'll have a fixed value of flux, that's it. Yeah, one thing I forgot to tell you is that the poles, their cross-section in theory should be rectangular or some well-known shape. In practice, we expand the cross-section at the end and make it bigger to get better efficiency. That expansion is called pole shoes. I'll show it to you maybe in some other pictorial diagram later. Pole shoes essentially mean a much bigger cross-section compared to the cross-section of the actual pole. It helps in improving the coupling to the rotating conductors, and that improves the efficiency. Efficiency, by the way, will be output power upon input power. In case of a DC generator, the input power is mechanical input power. Okay. And mechanical input power is torque multiplied by, omega. We'll come to that maybe later, but mechanical power is easy to calculate for a rotary input based on the torque and the rotation speed. So you calculate mechanical power input, you calculate the electrical power output, which is simply V into I, how much voltage is being generated and how much current is being drawn. The ratio of the two is the efficiency. To improve the efficiency is always a challenge. Losses here will be losses in the rotating conductors, which are going to be called copper losses, as we did in transformers. There will be losses in the core of the rotor, which are going to be called iron losses, as we did in case of transformers. Iron losses will be, again, hysteresis loss or eddy current loss. Eddy current loss will be reduced by using laminations in the core. A lot of things are similar to what we saw in transformers. Only thing is now we have rotation involved. On top of it, a third kind of loss would also get into the game because of the rotation involved, and that loss is friction loss. So input power minus all the losses will give you output power, as simple as that. That fact doesn't go away. Now, armature core is cylindrical, obviously. It is probably the most efficient construction from mechanical and electrical point of view. the material used for the core of the rotor has to have high permeability. That improves the coupling. If high permeability is not available in natural materials, we use, we impregnate the material artificially to improve the permeability. Stampings means laminations. Okay. Laminations, they reduce the eddy current loss. We have seen that in transformers. Same thing applies here. And it also helps in improving the construction. It's easier to repair a core made out of laminations compared to a solid core. Commutator converts the output signal into DC, that's for sure. It also helps in connecting the output to the external world. Actually, more correctly speaking, the conversion from AC to DC is not perfectly to a DC. It is from AC to a unidirectional current. I'll come to all that in my own notes. Okay, just take the word as it is for now. Lot of practical details, the shape of the commutator, the material, etc., etc. I'll try to show all that to you later also. Okay. Brushes. They are not rotating, but they are connecting to the rotating parts. The connection to the rotating part has to be of a conducting material, but rest of the construction is made out of non-conductors for a variety of reasons. Copper generally will break if you are connecting it to a rotating part for a long time. Carbon is generally more flexible, more malleable compared to copper. Carbon also has lower temperature coefficient because heat would be produced. When you are connecting brushes to the rotating part, invariably there will be temperature rise in the brushes. Copper doesn't handle temperature rise very well. So we make brushes out of carbon, except the portion which is touching the rotating part. There it has to be metal. Okay. If the construction is not done correctly, you will see sparks, etc. Brushes are one of the most fragile parts of the entire construction. They have to be replaced quite often. Carbon has very interesting properties which help. It is self-lubricating. It also changes its shape based on what is going on, etc., etc. So carbon is, practically speaking, the choice for carbon brush material, for the brush material. This is one picture showing you 4 brushes and the assembly holding them. Don't worry too much about remembering this, just appreciate that so much of mechanical engineering is involved in DC generators. Electrical engineers gave the theory. It is the mechanical engineers who made the theory work. Okay. Lot of details. Cooling fan, bearing, etc. I mean, I don't even fully understand everything, but just at least remember that there's a lot of details in the cooling fan may be necessary, especially in large power applications. EMF equation, I'll come to it later. Okay, we'll derive it ourselves. Now, types of DC generators. Obviously, there are several methods for defining the types. One popular method is based on how you are exciting the magnetic poles. We will assume that magnetic poles are electromagnets. That's for sure. There's no question about it. Now, you can have an extra DC source, maybe a battery a strong battery, of course, to feed current into the windings of the field, in the windings that are going on top of the electromagnets, that is field windings. Or since you are generating voltage from the generator anyway, why can't you just use that voltage to feed the field windings? That is called self-excited case. You don't need an extra battery in that case. Take the output from your own generator and use it to feed the field windings. So that is the second option we have got, self-excited DC generator. The first option is, of course, separately excited DC generator. Okay, both have pros and cons, but this is one method based on which we classify DC generators, whether they are self-excited or separately excited. That means field windings, are they being energized using separate DC source or using your own generator as a source? Now, suppose you are talking about self-excited case, then also there are several options. You can put the field winding in series with the armature winding. That's one possibility. There are pros and cons for everything, okay? Or you can put field winding in parallel or in shunt with the armature winding. That's second option. Or you can have a mixture of the two options. Part of the field windings in series with the armature windings and the remaining portion in shunt with the armature windings. That is called compound winding. I'll be talking about all this later in detail, which is good in what applications. So series wound means both field winding and armature winding are in series. Shunt wound means both the windings are in parallel. Compound means we have a mixture. Some portion in series, some portion in parallel. Lot of details again on these things. Now, as a generator, what are the things that matter to the rest of the world? It is easy to think that the electromagnets will produce more and more magnetic flux as you increase the current going in the field windings. In practice, it doesn't happen because the materials that you are using for poles saturate. After a certain value of field current, even if you put more current in, the flux would hardly change. Saturation comes in. So you should know when to stop increasing the field current. Theory apart, the reality also is there. No material can give you infinite amount of flux, no matter how strongly you feed the windings. So this is one characteristic that is described as no load saturation characteristic. That means the output of the generator connected to no load, and you are simply measuring the total EMF being produced. Plot it against the field current going in the field windings. You will see that initially E naught, that is the no load voltage coming out, will rise linearly with the field current. But after a certain value is reached, you will start seeing saturation coming in. And then E naught will flatten out no matter how high IF you try to put in. In fact, the wires may even break down if you put too high value of IF. Another characteristic that is important is how much current you are drawing from the generator. It is known as armature current versus how much voltage is being produced. Okay. How much EMF is being produced. And then actual voltage, as we saw in transformers also, there is always a difference between EMF and the actual voltage because of the winding resistances. That applies to DC generators also. So characteristic of EMF versus armature current and characteristic of actual voltage versus the actual current coming out. These two characteristics are extremely important for understanding how good or how bad a given DC generator is. Okay. Okay, forget this for now. Forget this also for now. I'll come to it later. Armature reaction, forget it for now. I'll come to it later. Again, lot of details. Let's forget it. I want to go. Yeah, commutation. Read this a little bit carefully. Idea is to convert the AC signal into at least unidirectional signal. No negative half. The negative half of the signal is converted to positive half. And that is done using a mechanical rectifier called commutation. I'll explain the functionality in my own notes in the next lecture, but at least understand the bigger picture, why it's there. Brushes connect to the commutator for sure. So their combination is always probably the most critical part of the entire construction. Damage, accident, etc. happen generally in that portion of the construction. Yeah, losses. A lot of things are similar to what we saw in transformers. But one extra thing that is there is friction loss and also windage loss. Because we have rotation involved, so wind will also have effect and it may produce some losses. Friction will be there for sure. Friction losses have to be accounted for. I don't have any equations for them, but we generally know based on the experience how much loss of voltage will occur because of one pair of brushes. So that number is generally known to us based on measurements. Iron losses, you know very well in transformers. Same thing here. The core of the rotor is what is producing these losses because it is built out of magnetic material. We have the equations to calculate hysteresis loss and eddy current loss. Stray losses, as I said, are the extra ones here, friction and windage. And on top of it, copper losses, of course. Okay. There will be field winding losses. I square R would apply to field windings also, as well as to armature windings. These losses change with load. Load means how much current you are drawing from the generator. These are the variable losses, and at high currents, they predominate. They produce most of the heat. Generators have to be cooled down using artificial techniques for high power applications. Fans have to be used for sure. If it's a very big generator, you may even have to use other techniques. Cooling oil, cooling water pipes around it, etc., etc. Okay. Yeah, we know all this. At least hysteresis and eddy current losses are known to us. So that fact is repeated here. Windage and friction are the extra factors here. I'm almost coming to the end of this one. Yeah, here are some practical applications of DC generators. Shunt generators means the field winding and armature winding are in parallel with each other. They are commonly used for these applications. They generally have better characteristics in terms of voltage regulation. The concept of voltage regulation applies here also. No load voltage minus full load voltage divided by no load voltage, divided by full load voltage, and the entire thing multiplied by 100. That gives you the percentage regulation here. That regulation is better for shunt generators compared to series generators. And that leads to shunt generator being popular in several applications like electroplating, battery recharging, because when you are recharging a battery, it's good to have a constant voltage, as constant as possible. Series generators have their own special advantages. I'll come to that later, but there are applications here for them also. They are not all that undesirable. In some cases, they are preferred over shunt generators. Motors, I guess we will talk about them later, but at least understand that the theories that govern motors are same as theories that govern generators, just that the functionality is reversed. For a motor, you give DC input to two windings, and as a result, mechanical rotation begins. The EMF generated in the armature is known as back EMF. That is the open load or no load voltage that you see across the armature terminals, across the two brushes. There's an equation for it. We'll derive it later. DC motors also, once you go to them, you'll see that they are also classified virtually in the same manner in which DC generators are classified, based on how the windings are connected to each other. If the windings are in parallel, we call it a shunt motor. If the windings are in series, we call it a series motor. If part of the windings are in series and part is in parallel, we call it a compound motor. That doesn't change. How to calculate power, etc., I'll come to that later. But one equation I want to bring to your attention is the top one. For a rotary system, if you know the torque and you know the RPM, the power is given by this equation. 2 pi n, capital N is the RPM, revolutions per minute. You divide it by 60, you get RPS, revolutions per second. You multiply it by 2 pi, you get omega, the angular frequency in radian per second. Multiply that by torque, you get power in watts. This equation will be used very often in the rest of the course for all motors, whether DC motors or AC motors. I'll prove it maybe in the next lecture once again. And there are other equations which right now I don't want to look at. Okay, so I think we are coming to the end. Testing of DC motors, just forget it for now. Motors also have a lot of applications. Shunt motors are used for these applications. A lot of them are there in our workshop in LNMIT. A lot of shunt motors are there. Drilling machines, milling machines, they are all using shunt DC motors. Lathe machines also. Okay, so I think I'll come to the end. Yeah, series motors have their own special advantages. I'll come to that later. Just see that these motors are not all that undesirable. They have their own specific niches. Compound motors have their own specific applications. This PPT is meant to give you an overview. Okay?